All right, so I haven't been totally honest with you. The truth of the matter is that light and electromagnetic waves in general are actually way cooler than I even let on. And the reason for that is there are properties of light and electromagnetic waves that allow us to probe the world in ways that you maybe even never considered before, and that until the last century, humankind never really considered. Okay? It used to be that the big power of light was that it would bounce off things, come into our eyes, and then we could see the world because, the light that bounced off things lets us know something about the stuff that it bounced off of, such that we can visualize via this apparatus in our brains what we're looking at, right? But the truth of the matter is there are these properties of light, interference, and diffraction, that allow us to see things at the very, very small, detailed level of nature that we would not have been able to see otherwise. One incredibly big example of this is this idea of X-ray diffraction and how X-ray diffraction was used to determine the shape and structure of DNA. This wasn't really illuminated until the 1950s. We didn't know what DNA was, what it looked like, what it was made of. We just knew that there was certain sequences in DNA that corresponded with certain traits. But we did not know how it was structured. And if you can't even know the structure of it, you can't sequence it, right? So you could say that this was probably one of the most significant discoveries of the 20th century. And it's all because of this property of light, of electromagnetic radiation, called interference and diffraction. And I'm excited to jump into it this week. Let's start with the quote of the week. It's from a woman named Tara Brach. And she says, "Pain, fear, and sadness are not wrong. Reacting to any of these emotions as if they were wrong initiates kind of a trance of unworthiness. The moment we believe something is wrong, our world shrinks and we lose ourselves in an effort to combat the pain." Okay? And I think this is one of those quotes that's pretty self-explanatory, but I'll just say, pain, fear, sadness, they're part of this whole ride that we're on, And I know from personal experience that it's so easy to take something that's just the raw experience of maybe a little bit of fear, that kind of fear that you have before a presentation or before an exam or before a date, right? And, make stories around it about how maybe you're weak for feeling that fear, or you're somehow broken, right? Or feeling depressed or sad, and then building a whole set of stories around that about how you're weak or you're broken for feeling sad. That's a whole bunch of crap that you're adding onto what is just a raw, normal experience of being a human being. And so whenever you see yourself adding on, that's really, that's the stuff you have control over, right? You have control over whether you want to pile on the suffering by taking normal human instincts like fear and sadness that are parts of this experience, and making those be about who you are as a person, because they're not. They're not. That's this doing that. Okay? And so see if, the next time you feel afraid or the next time you feel sad, if you can just hold it and sit with it and kind of cradle it like a little kid, and see if you can just accept that experience without saying anything negative about yourself in the process. Give it a shot. Okay, moving on. Why do we care? This whole DNA thing, I already said it. Moving on. Okay, so the first thing I want to share is that light is so amazing at probing the world, because really it's not just one thing, it's two things. Okay, if we look at light in a certain way, we see that it behaves like a particle. In other words, when we look at light as, the thing that lets me see myself on the screen, right, is something that bounces off surfaces and back in my eye, that's acting like a particle. It's acting like a billiard ball, right? And it's giving me information about the world, right? There's this other thing called the photoelectric effect, which if you shine light of a certain frequency at a photoactive plate, it'll knock off electrons. That again looks like, a particle, looks like billiard balls, like hitting one thing and another thing flies off, right? But if you look at light in a different way, like when you put light through a narrow slit, for example, you see it behaving like a wave. In other words, you get these little interference patterns. And we talked about this before, but these interference patterns happen because those, crests and troughs of the waves are either adding or canceling out. And we'll talk more about that in a second. But first, I would like to look at the various properties of electromagnetic waves, right? The things that they do, and talk about whether it's a particle-like or a wave-like thing, right? So reflection actually is both a particle and a wave-like phenomenon, right? Like if both waves can bounce off a surface and reflect, and particles can bounce off a surface and reflect back at you, right? Refraction. Refraction is primarily a wave-like property, right? You have interference. Interference is a wave-like property. Diffraction is a wave-like property. Polarization, which we've talked about, is a wave-like property. And this photoelectric effect, right, where you can bounce light off a surface and an electron will pop off, that's particle-like, okay? So there's something kind of fantastic about light, and that we can exploit it. I don't love that word, but yeah, we use light, we exploit light based on the various properties that it has, right? If we want to be able to, activate a photographic plate so that we can see pictures, then you want to use the particle-like property of a wave of light. And if we want to, get a better sense of the internal structure of, let's say, molecules, you can use X-ray diffraction, which exploits the wave-like property of light, and you learn different things, right? Light suddenly becomes this even much more powerful tool, okay? So let's talk about the one thing that makes this work more than anything else, and that's this principle of superposition, which allows for interference, right? So in the wave slide that we looked at last semester, I talked about how if you have, two waves like this adding together, right, then you get something called constructive interference, where this then will turn into a big wave where these crests overlap, right, and then a super small wave or a low trough where these troughs overlap, right? So two waves that are totally in sync with each other, okay? It's called in phase. Two waves that are totally in phase with each other will just create a new wave with twice as big of a crest and twice as big of a trough. Okay? All right. Now, this is constructive interference. Okay? There's another kind of interference called destructive interference, and that's just the opposite. Okay? If you have one wave that's like this, and then you have another wave that is like this, right? Then this part cancels out with this part, and this part cancels out with this part, and you're left with a straight line. Okay? So, granted, there's everything in between, like a wave like this could interfere with a wave like this where they're, make that a little bit out there, where this adds with this piece and this piece adds with this piece, and you get, some other, weird, like semi wave that looks a little bit different, right? But the bottom line is, what I'm trying to say here is that waves can add in certain ways such that they get brighter, like this, and waves can add in some ways in which they lose their brightness completely. It would be just like a dark spot. And other waves, they add in, it's like some mushy in-between area, okay? This is the principle of superposition. This is this ability to superimpose waves on each other and get new waves, some of which might be brighter, some of which might be blank, and some of which might be kind of dim, mushy in between, okay? And this is the lead-in to explain certain patterns that we see when we shine light on, you know, something as simple as two little slits, as we'll see in the next video, this Young's double slit experiment. And if we may shine light inside of actual materials or molecules, and be able to see what the patterns are that emerge from shining light through those, you know, geometric arrangements of molecules. And we're going to find out more about why those patterns form, how they form, and how we can at least a little bit mathematically predict what they might look like. Okay? So in the next video, we're going to explore Young's double slit experiment, which is probably the simplest version of exploring constructive and destructive interference and how light patterns will emerge from that kind of interference.